Hello students, my name is Shayan Mitra. I am the faculty member of Department of Electronics and Communication Engineering of Greater Kolkata College of Engineering and Management. Today is the last lecture of the module 2, where we have discussed the LTI system response for impulse and step signals. We have discussed earlier in the previous 5 lectures about the convolution sum, how the discrete time signal and continuous time signal can be realized using the impulse signals. We have understood with a different kind of aperiodic convergent signals the examples, how using the convolution we can determine the output signal. We have realized how the block diagram can be written, and we have given a simple examples of difference equation, and also we have described about the LTI system properties of LTI system properties and the convolution sum properties, such as deductivity properties, association properties, multiplication properties, and using that we have realized different kind of signals when fed to the a system, a data system, or fed to a specific LTI system, linear time invariant causal system, or linear time invariant system, we can realize the output. So what we have discussed in this previous lectures, we are going to continue with that specific understanding. That now we are going to discuss the causality and the stability of the LTI system. Okay, we have already discussed what is the causality of a signal, what is the causal signal, what is the non-causal signal, and it is very much similar here in case of causality of LTI system. Now the property will be now we will go direct to the mathematical representation here. The mathematical representation of a causal signal is that for causal discrete time LTI system, the condition implies that the convolution sum representation is becomes this: y of n is equal to k is equal to minus infinity to n x of k into h of n minus k. Okay, and the alternative equivalent from equation 2.43, we can write that y of n can be written as k is equal to 0 to infinity, where h of k into x of n minus k. Okay, so this formation, if you remember this mathematical representation, it basically same implication of this signal. Okay, and similarly for continuous time LTI system, is causal if h of t is equal to 0 for t less than 0, and in this case the convolution integral is given by this: y of t is equal to minus infinity to t x of tau into h into t minus tau d tau is equal to 0 to infinity, where h tau into x t minus t tau. For causal system, the value should be in between 0 to infinity, and no non-zero element will be found when we are talking about a negative integers. When n or the value, when we are getting a summation where the negative values are invoked, the signal value will be a 0, or you can say that no non-zero element will be found. Okay, so now if we proceed with that, so this is the causality of a LTI system is equivalent to its impulse response being as a causal signal. Now for stability of a LTI system can be rewritten as that mod x of n is nothing but the amplitude of the signal should be less than b for all n, where the value of b should be less than 0, and that condition will satisfy the stability of a system, or the system can be said, or the system can be said as stable if every bounded input produces a bounded output. So this is the bounded input. For that bounded input, we should have mod y of n, which has been written in convolution sum form, is summation of k is equal to minus infinity to plus infinity and h of k into x of n minus k. Okay, this formation, and for this reason we also should have a value of y of n should be less than infinity, and it could be written as this form also. Okay, that the value of h of k, summation of k where minus infinity to plus infinity should be less than infinity. Okay, so it could be conclude that if impulse response is absolutely summable, that is if the system is stable. Okay, but one of the important thing we need to understand here, that this specific condition where we are establishing a signal or system that absolutely summable, an impulse response which is absolutely summable, it will be a sufficient condition to be a system to be stable. But a system to be overall stable, we need to also have a output value mod y of n should be less than equal to b, where the b also is less than equal to infinity. So this is the total condition. This condition should be met only because of this condition. With using this condition, it's a sufficient condition to a system, sufficient condition for a system to be stable, but it's not the only condition which will be required to a system to be stable. With this condition, there is a sufficient condition to be a system to be stable, but a condition, if a system is the system needs to be absolutely stable, we need to have this condition where mod y of n is less than equal to b and the value of b is also less than equal to infinity, and this can be written here that k is equal to minus infinity to plus infinity where mod of h of k. Okay, so now if we the same process will also be taken care where we will get the value of minus infinity to plus infinity, integration of minus infinity to plus infinity where the limits are this, we are integrating the value mod h of tau into d tau where this value should be less than infinity. Okay. So in this way we will these conditions are sufficient to understand a system is causal or stable. Okay. Now as we are get into the unit step response of an LTI system, the unit step response of an LTI system we have already described how it works. It could be written with that specific notation of SN, step response is equal to UN into H of n. H of n is the impulse response of that specific impulse signal. Okay. Now using that formula, that this is the function. Okay, this could be written here. Now using this equation, we can write this equation: h of t is equal to d of st dt is equal to s of t. Now if we have to describe the causal LTI system described by differential and difference equation, we need to have the solution of second order. Now suppose this is a linear constant coefficient of differential equation. Any kind of differential equation can be rewritten as this d of dt of yt plus 2 into yt is equal to x function of t. Okay, so if we put these values properly in example, now we are going to understand this how we use a linear constant coefficient differential equation. We will use a problem or example. Using that example, I am going to give you the total explanation of what the differential equation is or the differential equation is and how it works. Okay, so this one of the important thing, this is a difference equation. Okay, where we have used the past input values. And now we are going to derive what is the differential equation is and how a differential equation can be used to understand a specific input impulse or input signal. Okay, so now suppose this is an example of our input signal which has been written here as k into e to the power 3t and into u function of t, and k is the real number, it means a constant. Okay, now we have you have understood the differential equation in the second sem in your previous in your previous sem in your previous session. So we have just jump into the solution of the specific input signal. Now as we know that a differential equation can be rewritten or can be rewritten as, or it consists two parts. One is a particular solution, two is a homogeneous solution. Particular solution can be written as yp function of t, and homogeneous solution can be written as h for homogeneous, it taken h for homogeneous, y of h a function of t. Okay, and so the output signal of this function can be rewritten as addition of particular solution and the addition of homogeneous solution. Okay, so first step is, as we understood that the particular solution satisfies the equation of 2.95. The equation of 2.95 is here, this. Okay, now for particular solution, what the particular solution really meant, it meant that the input signal is 0. It means a particular solution will only provide you the so-called forced response or the initial condition response, where we haven't provided any input signal. So For that reason, to derive or understand that particular solution, we will put x of t is equal to 0. By putting x of t is equal to 0, it means there is no initial input condition. So when there is no input signal in the system, we will realize that that system really has any initial condition or not. To understand that a system really have any initial conditions or the initial conditions are required or not, to realize those characteristics, we will use the particular solution. So first we will derive the particular solution, then we will derive the homogeneous solution, then we will add both of them. After that we will calculate the constant values or the constant values. After that we will conclude how the output signal can be rewritten as. Okay, so first we understand the output signal has been written here as a component of particular solution and the homogeneous solution. So first we will derive the particular solution. In case of particular solution, what I have discussed, that there will be no input signal, because without the input signal we will calculate that system does have any initial conditions or not. Okay, so if we start with it, that first this input signal will be 0. Okay, so for that reason, for particular solution, what we will do, this is the e to the power 3t. Okay, so first we will consider that, suppose that the regard of equation 2.95 that we have already discussed, that x of t is equal to k into e to the power 3t for t greater than 0. So ut is 1. So we hypothesize the solution for t greater than 0 of the form is particular solution is equal to y of e to the power 3, capital Y into e to the power 3t. Okay, where y is a number that we must determine. Now that's the first reaction, that we are going to determine the value of y. Now what we will do, we will put the y e to the power 3t value in the equation. The problem equation is this. So as we put the y e to the power 3t in this 2.98 equation, in this equation, okay, so what we will do, we will take a first order derivative of y e to the power 3t. We will find 3 into y e to the power 3t, okay, and plus 2yt. Okay, we will find 2 into y e to the power 3t, which is equal to k e to the power 3t. Okay, so using that, what we will, the e to the power 3t will take common of e to the power 3t, and it we will divide all the elements with e to the power 3t, and we will find 3y plus 2y is equal to k. From that we will find that y is equal to k by 5. So we get the value y is equal to k by 5. It means that value of y is also constant. So we'll put the value of y in the particular solution. So the particular solution will be yp function of t is equal to k by 5 e to the power 3t when t greater than 0. Okay, now in order to determine homogeneous solution, we hypothesize a solution of the form y of h function of t is equal to a to the power 3 st. Okay, now a to the power st is nothing but similar solution for the exponential. Okay, so now we will put this a to the power st value in the equation 2.98. The 2.98 is this, so we'll put the values. Okay, as will differentiate the function, and we'll get a to the power st into s plus 2, which is equal to 0. For homogeneous solution, the two steps that we have taken here, first we derive the particular solution. How? We have taken a value of the input signal in particular solution, where we have assumed that the value of input signal in t greater than 0 will be k into e to the power 3t. Okay, so we put that value in the first order derivative, and we found y is equal to k5, the constant. Now we put that value, so we will get the particular solution as k by 5 into e to the power 3t. So the first step is completed. Okay, the next step is we have hypothesized a solution where the homogeneous solution is very much similar to the input signal, and it could be written as a into e to the power st. Now that same value, we will put that same value in the first order derivative equation. So after the derivation, we will find that a e to the power st into s plus t, which is equal to 0. So now that from this equation we see that we must take s is equal to minus t, because we know that this signal is not 0. So this value should be 0 to be the net result. To be 0, we need to have s plus 2. This component should be 0. To make this component 0, to make the whole component to be 0, we have to take s is equal to minus 2. By doing that, we will get that we will get the homogeneous solution as a into e to the power minus 2t. So now, as we know that the specific the output signal is the addition of the homogeneous signal and the particular solution, or the homogeneous solution and the particular solution. So we will add both the value that we have extracted from the by solving the problem. So this is the particular solution, and this is the homogeneous solution. By adding them up, we get output is equal to a e to the power minus 2t plus k by 5 into e to the power 3t. For this condition only, we have to consider the condition where the t is greater than 0, because if the t is not greater than 0, we will not find any value. Okay, to get a value, we have to put a condition where the t is greater than 0, because the problem is showing that this is a step signal input. So in case of step signal input, the left-handed side region or the negative side region of a signal will only provide a 0 element. Okay, we will only have non-zero elements in the right side of the region. So by putting all this, now this is the step. Now what we will do, we will find the value of a plus k by 5. Now we will put the initial condition. We will put t is equal to 0. Now the initial condition only be found when we will put t is equal to 0. It means before the system started, we have to realize using the mathematical equation of a system where the system doesn't fed by the input signal. We can put that y t is equal to 0, means t is equal to 0. Now if we put t is equal to 0, the output will be 0. Okay, and these values are also zeros. Okay, from this we will get a is equal to k plus 5, and from that we get a is equal to minus k by 5. Now what we have to do, we just have to put the value of a in the whole solution. Okay, now by getting putting that, we get y of function of t is equal to k by 5 into e to the power 3t minus e to the power minus 2t. So this is the whole solution of the equation. It's basically the output signal. Okay, this is the output signal. Using the input equation, just by using this is the input signal. Just by, as we know how to get output signal using the first order derivative, we conclude the signal, or will extract the signal using the particular solution and the homogeneous solution. Okay, so these are the steps. The first, and we'll go through another example also. Okay, so this is the output of the specific signal. Now suppose we'll go through another example also. One second. No, we'll okay, so the steps that we have taken here is that first we will realize the input signal. Okay, next we know output signal will be the combination of particular solution and homogeneous solution. Now we know the first order system, we know the first order solution. To get that value, this is the homogeneous. To get that value, what we will do, we will first extract the particular solution by providing an equation for particular solution where it is very much similar to the input signal. Okay, by using that, we will put this value into the first order derivative and we will find the value y as k by 5. Okay, so I get the value k. Okay, we put that value, and as we will get that derivative, and in place of 0 we put the input signal. By doing that we get the y is equal to k by 5. Okay, so first we get the particular solution, and next we don't do the same process for homogeneous solution. In case of homogeneous solution, we will hypothesize a solution where we get a input signal very much similar to the input signal that has been given in the problem solution, in the problem. Okay, so we got k into e to the power 3t into ut. We take a very similar signal which is a into e to the power st, where we have two constants. Okay, so we have to find two constants. Here the two constants are a and small s. To find that, we will take the same route. We will put those values in the first order derivative. We will do the derivative and we will find the value is equal to 0. Because the homogeneous solution, in case of homogeneous solution, what we have? In case of homogeneous solution, we will always have the signal, input signal will be 0. For homogeneous solution, we will have the input signal 0. So by putting those values, we will get equal to 0, and using the comparative rule, we will find that how we will convert this whole equation into a form of multiplication form, and it will be equal to 0. So we always know that this a has a constant and s also has a value. So for that, only this particular element will be 0, that s plus 2 will be 0. For that, we will find that s is equal to minus 2 to satisfy this condition. Then we will put those values and we will find a into e to the power minus 2t as a homogeneous solution. Now we add up the homogeneous solution and the particular solution to provide us to get the output of this signal. Now you get this thing, and we know the condition that we are provided with, and after that we again put the value 0 in place of y function of t. Why we have done that? It has been described here, that if x function of t is equal to 0 for t less than equal to t0, then y of t must also equal to 0 for t less than equal to t0. It means we will find the value of a by putting hold on the system. We will get back to the initial condition where the t is equal to 0. Okay, now we are doing the t as to find the value of a. We already know that the condition that we have taken here as according to is very similar or likely to the input signal. By using the initial condition where the system doesn't fade with the input signal, we will put the value t is equal to 0. By doing that, we will find this solution from this specific solution, right? From this specific solution, we find this specific solution. By doing that, we get a is equal to minus k by 5, and we again put this value into the equation 2.106, and we will find the output signal. Okay, so this is another technique of finding the output signal by using the first order difference equation, okay, of a LTI system. Okay, and this LTI system, that now we have described all this process by which we can use the difference equation to find the output signal when the input signal has been given for a LTI system. And here what we are required to understand the why the linear constant coefficient differential equation is required. That now where y of t denotes the output of the system and x of t is the input. For example, comparison this. Okay, now how do we get into this conclusion here, that this specific impulse signal can be rewritten as this? So we can use this approach. Okay, h of t is equal to d of st by dt. So the first order derivative can be applicable to determine the output signal when the input signal is given for a LTI system. Okay, so this is the way we will conclude the module 2. In the next lecture, we are going to discuss. We will start the module 3, where we will discuss the Fourier transform, and also we will discuss the difference equations problems and the significance of that when we put them into the LTI system. Okay, so thank you.